All right, cool. Let's continue. So how difficult do you think a full chain exploit from the baseband to the application processor would be? We have Guy here today who's giving us an extension of some cool research that he presented last year at Syscan 360. And thanks.
So, hi everyone. Hi everyone. My name is Guy. I'm basically going to talk to you about baseband hacking today, and this is the second part of my talk, of which I gave the previous part in Syscan 360 last year. So just a few words about myself. I'm independent. I'm doing low-level research for the past couple of years. I'm doing Infineon for around 1 year right now, and I really like coffee. So just a few words before we actually dive into VR in baseband itself. Let's just do a small recap, just to get a better understanding and being on the same page together. So when we actually talk about baseband, we're actually talking about that small processor that you guys have in your cell phone, either in your cell phone or in your car or in your connected device, that basically that thing that. Sorry, I'm really nervous. I'm a very shy person, so it takes me a couple of seconds just to wrap up and basically get it. So you have this small processor in your cell phone or connected device or car or whatever, which basically gives you some kind of WAN connectivity outside. And if you basically lose it, you don't have that thing, and you only have Wi-Fi, Bluetooth, or NFC. So if we take this picture from the iPhone 7, so that yellowish thing or orange thing on the top under the A10 would be the baseband. And this is the main chip that I was actually working on, and I still continue working on for the past more than 1 year or so. And if we actually look at the market cap of baseband, we basically see around 6 major companies doing that, and that would be Qualcomm, Samsung, Intel, Huawei, Unisoc, and MediaTek. And right now, Qualcomm is probably the largest company doing that, and probably the major company doing basebands, or at least the one manufacturing for cell phones. But when I actually started doing this research, my main question was basically to answer how hard would it be to get a full chain directly from the baseband to the application processor compared to the one that you would actually do from WebKit to the kernel over there on iOS. Back then, basically, iPhone basically worked with Intel or Infineon exclusively, so Infineon was a really good target rather than working on the QDSP, just like Dimitrios spoke yesterday. So reversing ARM seemed much easier rather than reversing QDSP, so it seems like a nice target to start looking at it. So just a few things about my previous presentation, what I did, where I failed, and lots of failures, and lots of successes. So I actually managed to map the baseband from 0 to hero, basically understanding what kind of operating system is running over there, what kind of tasks, what kind of protocol stacks, and what kind of statically linked libraries. I wrote a few fuzzers that can actually interact between the baseband and iOS or Android. And since I was a telecom noob, and I guess I'm still telecom noob, I've understood telecom a bit better, since this is a completely different animal rather than the regular TCP/IP world that we're actually working on. And since this is actual research, so I failed quite a lot, and since I've been doing a lot of fuzzing on the device itself, I actually managed to burn one device. I got ripped off in $500 by some crackhead on eBay, and since this is actual research, I got really frustrated doing that. So just a quick thing before we actually dive into all those other stuff and start looking at it. So the main question that usually people ask me about it is, how can I actually get the firmware for the baseband over there? So basically, you just go to ipsw.me and you fetch the firmware. You have a zip file archive, and then you find a file called ICE, which is basically the Infineon baseband. This is basically just another zip archive that you have over there. And for the rest of the information, you can see it on my previous talk, which basically explains what's actually going on over there and what's actually running over there. And just a general architecture eventually. So on the right side, we have either iOS or Android, which is actually running on the application processor. And then we have some kind of shared memory connected either over SDIO or PCIe. And on this side, basically, we have the actual baseband over here. So we have some kind of real-time operating system called ThreadX. On top of that, we have Intel's SDK, which is UTA, which basically abstracts the firmware or the hardware from the actual tasks or processes themselves. On top of that, we basically have all the layer 1 and layer 2 handling, which basically talks to all the DSPs over there, and then you have all the tasks or processes that Infineon actually has. And this is really where all the actual juicy processes, things are, or these are the stuff that you actually want to audit. And on the left side, you have all the remote protocols over there, so like GPRS, UMTS, LT, and other stuff like that, which would be our main topic today. So our main goal would be basically just remotely attacking the Infineon baseband, getting some kind of code execution, and then jumping back to the AP itself. I'll be mainly discussing about the whole process of getting code execution on the Infineon baseband itself, and jumping is something else. And if we divide this kind of attack vector, we could basically divide it into two main attack vectors. The one that we'll actually talk about would be like a rogue base station. So it basically means you have to be pretty close to the target. You get the target to roam into your own network, and during that roaming and during that registration, the target would register to your own network. You'd find some kind of vulnerability over there, and then you get code execution and you jump off to the AP. The advantage about it is basically that you have full control over the network. So any kind of so the advantage about this kind of thing is that you have full control over the network and full control over the whole layout they're trying to give over there. The disadvantage about it is that you have to make the target actually roam into your own network, which sometimes is not that trivial, and with LTE and 5G coming up, it becomes even harder. The other attack surface over there is basically like a fully remote one or a core network one, which basically means finding some kind of protocol that the baseband has over there which gets rendered automatically. This wouldn't be like some kind of network registration vector or anything like it. It would be something like an SMS or an SS or something similar, and find some kind of parsing issue, use after fear type confusion, and then get a code execution and jump off to the AP. The advantage about this kind of thing is that it can be done fully remote, and it's pretty good, but the attack surface over there is pretty hard and it's pretty small, so it's not that trivial to do it. And this is where I actually started understanding what's going on over there. So when I actually started doing this research, I actually did most of the stuff on iOS over there, but as my research actually grew up and became bigger and bigger, I basically understood that this research actually applies to any Infineon baseband running over there. So basically, any iOS or Android or anything similar like it would be probably applicable for that. And any framework that is basically running the Infineon ones basically share a lot of code over there, and most of the stuff that they were actually sharing would be the remote protocols over there. This basically means that any protocol or any parser on GPRS, LTE, UMTS was basically identical between the iOS and the Android side. So this was basically my goal in understanding over there, what's going on over there, and trying to find something over there. So ideally, what we want to do is basically we would like to start mapping all the remote protocols which we have over there. We'll pick some kind of protocol, and then we'll try to find something over there. When I actually started doing that, I didn't really know a lot about telecom or much at all. So I was basically doing a lot of reverse engineering. I was skimming a lot of things. I actually looked at it, and I found a lot of problems over there, but I didn't really understand what's actually going on over there. And I didn't really understand what kind of context it's running over there. So I was looking at reverse engineering. I was looking at assembly or C code over there, and I was like, okay, so I have no idea what's the actual context over there, but it sounds pretty interesting, and it looks like it has lots of mistakes over there, so I should probably take a look, even dig deeper. And the thing that I actually found over there was basically a shitload of auto-generated code. It means that Infineon basically most of their handlers were basically auto-generated by other guys or some kind of compiler or something similar, and this basically led me to understand that it could be much more error-prone than I actually thought. So basically, in order to better understand what kind of context I'm actually looking at, I basically started reverse engineering the boot process of Infineon again. And what I actually found was basically that there is some structure called boot entity, and it gets initialized just after Infineon finishes doing the boot process over there. And that boot entity eventually contains all the logic or all the entry points for every remote protocol over there. So if your basement basically supports for GPRS, UMTS, LTE, or anything like it, it would have an entry over there. And if we look at it over there, we basically have PSI_rambin, which is basically the original bootloader over there, which flows the sys_sw.elf, which is the Infineon mains binary over there. This binary basically does all the board bring up over there, and it creates one task called bootman. Bootman basically does the core initialization because Infineon is dual core, and once you finish that, it spawns one thread called CPS stack. CPS basically stands for Cellular Protocol Stack, and Cellular Protocol Stacks basically just iterates all over those boot entities doing that. And this is basically how it looks. You basically have the initial function, which for initializing the CPS stack, which basically initializes GPRS, LTE, UMTS, and everything else. It's a pretty easy struct to look at, and you can basically see the text over there and to better understand it. And if you look at the initialization function, you pretty much see that it's pretty easy to spot this one. So once I understood that, I basically saw, okay, I have a huge structure of array over there that contains all the stacks over there, so I can basically just start reverse engineering them and get better understanding. So after doing that, I basically started reversing lots of code over there. I mainly focused on LTE, UMTS, and GPRS, but as I actually progressed over there, I basically understood that I have almost zero chance in actually finding something if I wouldn't really understand what those protocols are. I mean, how does a cell phone actually get a phone call, or how does a cell phone actually get an SMS, or what happens when a cell phone goes on to get some internet, gets some internet connection? So I was really frustrated about it, so I was like, okay, I should probably consult with a friend or something, and basically he was like, yeah, guy, you shouldn't reverse that much, you have the protocol stack, so just read the documentation over there and try to correlate in between together. And my original answer to him was like, okay, what the fuck? Why should I read documentation? I mean, I really like reverse engineering. I should really just continue reversing until I actually understand that. But I was really wrong about it, and eventually just reading the docs and correlating between them was the actual solution. The problem with that was that because you have so many specs and you have so many protocols, so you feel kind of lost about it, because every option you have over there, if you want to look at GPRS, UMTS, ETWS, SMS, SS, and probably a lot of other acronyms, there would be documentation for that. But actually finding and correlating and finding a real solution or a real focus for that is not that trivial. And during that time, I actually felt really lost about it, because I had a lot of data which I reversed, and I had a lot of documentation on the other side, but I wasn't really able to find the correlation between them, and I felt really lost. So eventually what I did, I got to protocol stacks, and I was like, okay, LTE is pretty new at the time, and GPRS is pretty old, so the legacy code is good, it probably has lots of bugs over there, and LTE is pretty new, so new code means more bugs, new bug classes and stuff like that, so I should actually focus on both of them. And eventually, I mean, looking back, it was kind of a mistake looking at it, because most of the initialization paths over there were quite identical, but eventually I did manage to find a few things, so it was all right. So if we actually dig deeper, we have on the one side, we have basically a shitload of reverse engineered data, and then we have the specs over there. And the real idea is basically getting all the data from the reverse engineer code, from the binary code over there, and correlate it between the specs. And the specs actually mention something called OTA messages or over-the-air messages. And these messages basically state what kind of operations either your base station, your core network, or your cell phone wants to do. So for example, if your cell phone wants to get an SMS, start a call, go online, or whatever, it will probably send an OTA message either from the base station or from the cell phone itself. And this was basically the ground point or the break-even point where I actually finally started understanding what kind of binary code it is and what's actually going on over there. And it was pretty nice to look at it. And, sorry. And inside those kind of stuff, I mean, when you look at it, you basically see that the specs are actually mentioned for the fields that are inside those OTA messages. They basically mention something called information elements, or IEs. And these IEs are basically say what kind of fields or types would be inside this message. So the specs basically mentioned that each element had either a type, either a value, or either a length field over there. And they basically mentioned that each of them could be either mandatory or optional. Obviously, I picked looking at the optional fields because I thought there would be more error prone over there. And you can basically combine them, like having a message that would have TLV, like type, length, value, and obviously you could add some kind of type confusions or similar stuff like that. Sorry. So eventually I actually managed to find a few interesting things over there when looking at GPRS specs over there. And the GPRS specs basically mention a pretty simple state machine when your phone actually goes online to get some sort of internet or something like it. They actually mention something called activation context or context messages, and these kind of context messages bring a few pretty interesting primitives like registration, activation, modification, and registration. And if you guys find it pretty interesting or weird, this would be like allocation, deallocation, free, and another allocation option. So I found those kind of stuff, and I basically started looking at it, hoping to find some kind of interesting optional value or some kind of variable length value. And while looking back at those kind of stuff, I was like, okay, so I'll find a variable length message, and then I'll try to corrupt it in some way, instead of actually looking for some deep bugs that would be more like state machine dependent or deep architectural bugs. And when I look back at it, I mean, this strategy is pretty shallow, but it actually worked. But I mean, a year passed since then, and things have pretty changed since then. So I wouldn't assume that this strategy would actually continue working, but it was nice looking at it from that. So eventually, I actually found a few candidates that actually give this kind of messages. So I found a few variable length messages that there were over there, and I could basically shape my layout using some kind of registration context. So it basically meant that I could it basically meant that I could actually control the allocations by sending either request, accept, modify, or reject messages to the cell phone, and then I could basically shape my layout using that. The actual message that I actually found over there was basically an information element capped by the specs, capped by 100 characters, but the length was actually transmitted by the network, so I could actually control it on my own. And this is basically how it looks like. So you have the parameter of the length over here, you have the static allocation going over here, and then you have a classical linear corruption going over there. So obviously at the start I thought I could actually control everything on my own, but eventually I actually found that it's capped to 255 bytes. At the time there was no ASLR, although new Intel modems do have some kind of ASLR, but they're missing quite a lot of information. The allocation was done on the heap, so there were a few integrity checks, like some kind of magics, which are all deterministic. And the question which I actually thought to myself, what kind of address would I actually want to overwrite once I get code execution, was something that I need to answer on my own. So without actually going on the exploitation itself, or the post-exploitation itself, because it would take a bit longer than that, I mean, we initiate a lot of request messages to the cell phone over there, and then we shape the heap over there. Then we do a modification request where we do our linear corruption over there, and the next time the phone is actually asking, okay, can I actually activate the context over there, we basically send a reject message that would trigger the free operation over there. Once we do that, we basically send another request modification to the cell phone, and with our own free PTR that we can actually control, and using that, we basically gained a write-where primitive using that. Eventually, I picked to overwrite one of the USB or Lightning pointers on my own and get code execution, and that was it, basically. So the thing is that this was fixed or banned about 1 year ago or so. When iPhone XR or XS actually came out, Intel came with a pretty interesting surprise. Up until now, all the basebands were basically ARM-based, but the newer ones were basically Intel-based, or some project called Sophia. So these basebands were actually pure Intel x86 basebands, which basically meant a whole different, a full recompilation of the UTA infrastructure over there. They added some kind of ASLR, and they all started using the safe libraries, which basically meant that they started using memcopy_s. Not sure if Intel is going to continue doing that, or maybe they'll go back to ARM. Only time would actually tell. But I imagine that they already knew about this bug, and they didn't really care, because if you kept reversing enough, you would actually find it. This is basically how I found it. And this is basically how the fix looked like. So they just added a few bounce check and using memcopy_s over there. So this thing is pretty problematic eventually. I mean, I could keep reversing and keep doing that, but newer iOS would actually go out, and I'd rather spend as less time as I can reversing things rather than doing ODE or VR over there. So, and reversing that much for one bug doesn't really scale that well, and I need somehow to scale my research to do that better, or do things easier eventually. So ideally, what I say in pretty beautiful words would be, I want to scale my orders per day scale, or in less beautiful words, can actually fuzz Infineon to get more out of it, or to scale my research in some way. And I've never done too much in embedded on my own, so this was basically one of my first attempts, and these were basically my main goals. I mean, the bugs I found was basically just a shallow bug, so it's pretty easy to find, it's pretty easy to fix. It doesn't really require that much of understanding of how the protocols actually work. And what I'm doing right now is basically trying to find harder bugs, which are most architecture dependent, which are harder to fix, and they require like deep understanding of the whole protocols and on the state machines over there. And ideally, what I actually want to do is basically just fuzz Infineon, let it run, see if I have interesting crashes, see if I have interesting path or some kind of test cases, and these are basically my attempts on trying to do that. So, sorry. So my first attempt was basically just throwing the Infineon baseband into QEMU, trying to do the board bring up over there and trying to understand what's actually going on over there. I was really curious how hard would it be to actually emulate this kind of thing, because eventually it shouldn't be that hard, right? I mean, you need to do some kind of board bring up over there, you need to have the same address space and some kind of peripheral emulation over there. But apparently most of the work over there was basically doing the board bring up over there, because it starts from a different core which loads the bootloader, which loads another bootloader, and then jumps off to the main binary. And I was mostly focusing on emulating the main binary instead of all the other bootloaders over there. So I kind of failed miserably doing that, and I gave up pretty quickly after a few weeks. My second attempt was basically, okay, so if I can't fully emulate everything, I'll probably just get some kind of RAM dump and then continue from the same state over there. Back then, I didn't really know I could actually get a RAM dump, so I was like, okay, I'll start looking for that. And basically, my main thing was like, okay, in order to get a RAM dump, I want an ODE, so I need to get a RAM dump. And in order to get a RAM dump, I need to crash it. So in order to crash it, I need to find an ODE. And it was like a cat and mouse thing that I was like chasing myself eventually, so I basically gave up. So the third attempt was basically the most successful one eventually, because I was like, okay, so I can't emulate everything, I can't continue from a specific state, but Everything that I'm basically auditing right now is basically just parsing data from one place to another. So these state machines are pretty small, around 400 to 3K functions. So theoretically, I can basically take all those functions and just glue them together and in my own space or whatever you call it, and just plug a fill to it. And it actually worked. I mean, I did a lot of reversing and lots of type inference over there, so I had most of those things ready. I wrote some DFS algorithm which iterates from the interpoint of some protocol stack over there, generates one huge C file. I added a lot of malloc, queues, interrupts, and stuff like that. And then I basically recompiled everything, put everything into QEMU, and it worked. I was really amazed about it because I didn't really think it would actually work. So here's kind of a demo of it, which I hope it will happen. So this is just one of the protocol stacks. Oh, fuck. So, not sure if you see it, but they compiled right now. Just a few more like replaces and some header files. And so this is basically AFL running the binary I just generated. Symbols. Fuck. Oh, shit. So I really hope you liked it. Any questions?
So you got the code emulated and running and fuzzing. Did you get any bugs out of that process?
Did I get what?
Any bugs? Did you find any bugs once you
So
had it?
I got like 1K crashes or so up until now, and I need to track it. But yeah. I mean, my main goal is now trying to make it faster because I'm only getting 1K execution per second, so I want to make it faster.
Thanks.
Sure.
How do you deal with the states that the firmware is in? So if it is like already connected to a base station or not, and so on?
So what I did was basically emulating a few parts over there. I'm emulating some kind of small SIM card which basically says, okay, this is already connected to GPRS, or this is already connected to another network. So it's already there in some kind of function which basically tells him, okay, this is the context you want to look at. Does it answer it or not? I mean, okay, so what specifically? I mean,
you might have very different states.
yeah, you're right. You're right. It's not that simple, right? It's very fragile.
You mentioned that the newest 5G version is all open source. Have you looked to see whether the protocol implementations in the open source version are the same as in the version that you're looking at?
Open source, sorry?
Didn't you say that the new x86 baseband has an entirely open source, or
No,
did I misunderstand?
No, I wish. I mean, basically Intel have a lot of shared code in their SDK over there, so most of the libc library is open sourced over there, so you can generate fleet signatures or just diff it on your own to get better coverage. So,
I was just wondering how you kind of patch up any structures and stuff that are needed from.
Sorry?
I was just wondering how you patch up any structures that are needed from like the initialization process.
So I didn't. I just took a specific parser out of it. I mean, I took one parser which basically parses like SS messages or SMS messages or like mobility management or GPRS mobility management, and this was basically my entry point. And I wrote a few abstraction layers to basically abstract all the malloc operations, queues, and interrupts on my own, and just glued it over there because most of my code had pretty good types over there already, because I did lots of reversing before that. So I glued it together, and it kind of worked.
Okay, so you didn't really find that there was it had a kind of lots of requirements on, I guess, kind of back to the question earlier, like the state of the system as a whole, like the parsers were pretty independent, were they?
I'm pretty dependent because UTA abstracts most of those things, so I can just override those functions and just do what I want eventually.
Have you started putting together something to attempt your exploits on, well, test exploits you find on the real hardware, like communicate with the baseband through radio?
This one, the thing that I showed. This was tested. I mean,
So then,
sorry?
well, what are you using to test it? Like a software-defined radio, or what's your setup?
Yeah, like a B200, yeah, USRP.
No more questions?
Right?
Thank you.
Thanks.